This was pretty good, I thought. Not arranged, it was spontaneous, yes. All right, so our next speaker is going to be Maria Gastiasoro from Donostia in San Sebastian. You should be friends with Maria because San Sebastian is a very nice place.
And I'm looking for PhD students.
And she's looking for PhD students. How about visiting collaborators? Okay, please go ahead.
Yeah, it's fine. Okie dokie. So, let's see, this one. Yes. Okay. So now you can hear me, okay? Well, first of all, let me thank the organizers. My first time in Brazil, I'm enjoying it very much. It's my second day, so I'm mostly going on caffeine, like the jet lag is the worst, but please bear with me. So today I'm gonna talk about something a little bit different that has been discussed now, until now, about the electron-phonon coupling. And first of all, let me start with the acknowledgements. So this was work that sort of started right before I was leaving Rome, and now each of these people are in a different place. But most of the calculations that I will be showing today were done by Julia, who is now in Geneva with Luke. Okay, so electron-phonon coupling, typically when we think about it, it's in this sense of you have some electronic spinor that emits or absorbs a phonon. And the usual way of thinking about this interaction is spin-independent term. That is, if you have a spin up, you interact with this phonon, you'll still end up with a spin up and exactly with the same amplitude if the entire process happens from down to down. Now, this is the typical starting point for studying phenomena such as CDWs, superconductivity, transfer phenomena, and so on. This is really weird. It's like really high. Oh, yeah, I'm tiny. Okay, a less common way of thinking about electron-phonon, which is what I'm going to be discussing today, is by spin-dependent vertex, okay? So I'm showing it here. You come with some spin, you interact with your phonon, and this interaction vertex knows about the spin. And this is way less common. As far as I know, it's been mostly studied in the context of whenever you have magnetism, if you have some type of inversion breaking, whenever you have spin-orbit coupling, and so on. This is some references here. This one is very connected to the one I'm going to talk today, and also Thais in the audience was part of this project. So while I was going through, scanning through the literature, which, by the way, now the previous speakers has freaked me out because what I'm about to present is not, we haven't posted it yet, but I guess I should rush. So there is some recent work that are now starting to look into what type of physics of phenomena one can have once you get this type of, spin-dependent electron phonon. So in this case, they did some fancy sign-free quantum Monte Carlo phenomena, and they saw that you get some staggered spin loop current state and so on. So what I'm going to discuss today, what I'm going to show you today, is a way to get this type of spin-dependent matrix element, and I'm going to argue that potassium tantalum oxide, it's maybe a good platform to realize this type of interaction. And the way I'm going to do that is by showing some DFPT, so some ab initio results, and I'm gonna use a lot or develop a toy model because I sometimes so ab initio can be really useful, but sometimes to me it can feel a little bit like a black box. So developing this type of models helped get lots of microscopic insights. So let's start with the motivation. Why is it that we're looking at potassium tantalite? So this is a relatively new family of superconductors. They come in, for now at least, in super or in heterostructure form. So you have the material, they put different layers and different stuff on top. They get some, this is still not something where there is consensus. There is two-dimensional electron gas. Some people say it's quasi-three-dimensional electron gas. Nevertheless, you get a metal, and if you cool down to around 2 Kelvin, it becomes superconducting. And many people got very excited a few years ago, because it superconducts at 2 Kelvin, and up till that point, the other platform that is of a system that is very similar, but instead of potassium tantalate, you have strontium titanate. It had been very well studied, and it was also superconducting, but at an order of magnitude lower TC. So people got very excited, and one of the themes that you find in all these papers that people point out, not sure, I mean, why, but tantalum is a 5D, so you have 5D electrons. In KTO, in strontium titanate is titanium, which is 3D electrons. So, spin orbit coupling is much larger in tantalum, and many people were saying, well, maybe this has to do with, there is some role, like what is the role played by spin orbit coupling? This is something that I'll say a few words about this, at least today. The second thing that I would like to highlight is that there was something very unusual happening where they found very different TCs, and by very different is either there is TC or not, depending on how you grow these crystals. So if you grow let's say you grow something on top along the crystallographic direction 111 versus 110 or 001, then you basically get 2 Kelvin, or in the case of 001, nothing. Okay, and then in the one in the middle is somewhere in between. So there is a strong dependence of TC on this surface. And the last thing I would like to highlight, that I'm also going to mention later in the talk, if I have time, is that there is like a really strong violation of Pauli limit. So maybe you've heard that when, at least if you have a conventional singlet superconductor, you apply a field, the electrons will start aligning with the fields, and eventually you break the Cooper pairs, and at that critical field, the superconductor is destroyed and you go back to the normal state. So this is, let's say, Pauli limit. So for a given TC, you can estimate what the critical field would be expected to kill your superconductivity. In these systems, there is reports, this is the latest that I could find, there is of Andrea Caviglia's group in Geneva. They find, ratios of above 10, like really strong violation of the Pauli limit. So what about the pairing mechanism? This is the last thing that I'd like to mention about this system. It's not settled, I would say. It's still under debate. I would like to highlight two ideas. One of the first one is pairing mediated by ferroelectric modes, and this is because this system is very close to a ferroelectric state, a polar state, if you wish. So there is, just like we've been seeing up to now, all these, like you have a spin density wave or a charge density wave of some order or nematic ordered state, and you get fluctuations that can mediate a superconducting state nearby. The idea here is the same, but now you have ferroelectric modes, and these ferroelectric modes are transverse optical phonons. Okay, and coupling to transverse optical phonons is not easy. Typically, or historically, it's neglected, and I'll spend the rest of the talk basically showing how you can get that in the system. But importantly, going back to the experiments, it was very recently measured that these ferroelectric modes, these transfer phonons, as a function of temperature, they go soft, 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 and eventually they level off. So the system never goes ferroelectric, but is really, really close by. And this happens both for the bulk and for the surface in these systems. So if this mode is mediating pairing, maybe like let's see how the electrons couple to it. So that's where I'll get to now. Okay, so before going into getting numbers, I think it's useful to look at the problem from, starting from what should we expect from symmetry. So let's say that I write the electron-phonon form, where I have my electron-phonon as I wrote before with something. This is the conventional spin-independent term and some spin-dependent term. And in in KTaO, I have several modes at the zone center. The lowest energy one is the one that I just mentioned, the soft ferroelectric or transverse optical mode. All of them are odd parity, so T1U or T2U. So this is like a polar mode, or like a dipole, or an octopole, I guess. This is L equals 3. Now, if you want to get intraband coupling, so say that you scatter from the same band to, from within the same band, then by symmetry, because these modes break inversion, this term has to vanish. So this is the conventional one, is not allowed. This is probably why typically it's been neglected. But you can go to this other next term, and it turns out that the coupling to these T1U modes has this RASPA-like form. And so basically, this is like you have this is a phonon, so this is like a dynamic displacement of the lattice that is creating RASPA field, so some kind of magnetic field that is coupling to the spin of the electrons. And I'll show later how one can get it. But just from symmetry arguments, you can write down the allowed coupling, and it is like this. So it is allowed. Now the question is, how large is this? And the same for this other mode. So I'm just writing it for completeness. So this would be more like a Dresselhaus type of coupling. So you can imagine that if any of these modes were to freeze, then your electronic bands, if they are degenerating the paraelectric system, then they would split, just like in what happens in the conventional RASPA, let's say. Now for interband, unfortunately, this game is not so easily explained. It basically depends on the parity of the band. So in general, this doesn't have to vanish. Okay, and so now let me say a few words about the electrons in the system. So I told you about the phonons, so the modes that I'm going to couple to, which are odd parity. Now the electrons, the electronic band structure is shown here. It's fairly simple, I would say. It has 3 bands, 1, 2, 3. This gap right here is the spin-orbit gap, which is about almost half eV. It's really, really large. It's telling you that you have tantalum, so this maybe not so surprising. So the full lines are, ab initio, the dust lines are a tight binding model that you can get by using T2G orbitals, so these 3 orbitals that have spin 1/2, and that are spin-orbit coupled. So basically you have some hopping between the orbitals that is spin independent, so the typical hopping, and then you have some spin-orbit coupling that leads to 3 doubly degenerate bands, n equals 1, 2, and 3. So if you, for instance, now look at what is the eigenstates of this spin-orbit coupled band, you have things like, I don't know, Z up minus I, this is X down, or on the opposite. So this would be pseudo spin up, pseudo spin down. These are the degeneracy of these 2 states. Okay, so now you see the spin up and down are going to be combination of the original spins of the orbitals. Good. So now we go to the big machinery, the density functional perturbation theory. You basically move a little bit the atoms around, and you compute. We had to do, like, there was some in-house modifications that had to be done, but basically you compute this element here, which tells you how the electronic bands are affected once you move the atomic, the lattice displacements around, and that gives you, it basically gives you the EPC matrix. Okay, so the first result I want to show is that, as we were expecting for the intraband case, for all the modes, you can write the coupling in this form. That is some function of k, which is going to be odd in k, and sigma z. So this is the spin dependent. And the second thing I'd like to point out is this is the coupling for two of the lowest bands for the three modes, and it's the numbers. So from ab initio, it looks like the coupling to the lowest mode, this ferroelectric fluctuations, so ferroelectric mode, is huge in this system. And then the coupling to this octopole is also rather large. Okay, so how do we understand these results? So we are basically moving the lattice around, which is a non-magnetic operation, and it breaks the inversion if you want that. But how does sigma appear? How does the spin of the electrons appear in the vertex? So I'm gonna show two ways you can get that. First, I'm gonna give, I guess, the one that has been used the most in these systems, but I think it's the least intuitive one, but let's start with that. So I'm gonna call that orbital RASBA. This was a term coined by Indranil Paul, who was initially very puzzled by these results. So let me try to go through it. So you start with some, your phonon is you're inducing a displacement, so that displacement is illustrated here. So the oxygen atoms should be on the bond, and if you have a finite displacement, now there is a new hopping term between the T2G orbitals that was not allowed, and it's allowed in the presence of the hopping of the phonon. It breaks, or it's odd parity. It's sort of like has this sign form, and I'm just coupling two different orbitals. So in this case is the Z orbital and the X orbital, and this is sigma 0. So this matrix element doesn't know about spin. There is nothing that, I don't need spin orbit to get this. Now, I told you that the electrons, they are not orbitals, but are spin orbit coupled orbitals. So when I do a transformation to this spin orbit basis, this matrix or spin independent matrix element becomes or acquires spin. It becomes sigma y, and this, in this particular case, so for band 1, it becomes 4/3 Tu, where Tu was this non-relativistic matrix element. And then you can do the same thing for the other bond, and basically you can see that for k going to 0, this thing becomes kx. So if you combine both bonds, basically you get g kx sigma y minus ky sigma x, which is the RASBA type of form. So I start from something where I'm just doing this interorbital hopping, which does not depend on spin orbit, and then just when I go to the transformation of the, if you want, of the electronic bands, I get something that is RASBA-like. And this is, by the way, so there was some discussion in a few of these works saying this is all you need. Like in this system, you never need anything else. Like that's, the spin orbit is really not relevant for any of this coupling, and you should just think about it as having a transformation for the electrons. And it turns out this is not quite true, because there is a second process that you can have in principle that will give you also this RASBA type. And this is maybe the more natural way of looking at it, which I'm going to call spin RASBA, because here what the phonon does when it gets active, it creates new hopping terms that are now flip the spin, right? So now I have, in this case, I don't change the orbital, but I start from spin up and I go to spin down. So this is a spin flip. So this is directly something that is proportional to sigma x, and I can only have if I have relativistic effect. So if spin orbit coupling is finite. If I switch off spin orbit, this thing goes away. This one, it's, is still finite. So again, I do the same exercise, and I say, how does this type of process, what type of electron-phonon coupling does it lead to in the relativistic electrons? And again, so I start with sigma x, now I end up in sigma y, so I end up with the same form as the orbital RASBA case. Now, again, sign of kx. For the second band, another sign of kx. So basically what it's going to do is it's going to renormalize this first EPC coupling, and it's going to give something to the second one. Right? Now the question is, I have these two mechanisms, if you want. When I go to the ab initio results and I see these large numbers, what is the process that dominates? And it turns out that in KTaO, it depends on the mode. So for some modes, these type of processes are totally fine, and I can forget about spin orbit. But for the transverse optical soft ferroelectric mode, that is not true. So how do we know that? It's not like, in principle, relativistic DFPT gives you the answer, and it's not easy to disentangle it. So what we did was, okay, what you can do is non-relativistic calculations. In that case, only this type of process is allowed, and what you can do is extract TU from non-relativistic computations, and I'm going to do that for two modes, and both modes I get what I would expect. So this, in this language, now it is this orbital, so it mixes the orbitals, so it's an interband term. By the way, with frozen phonon, we could not get this before. This is one of the strengths of the FPT, that you can get both intraband and interband couplings. So you extract the number from here, you extract TU for one mode, TU for the other. This is completely non-relativistic. And now you go back and you have your good description of the electrons, and you project this TU on to the relativistic electrons. So what I'm going to do is I'm going to fix the chemical potential. I'm going to draw the electron-phonon coupling, the EPC, around band 1 and band 2. So I start first with the S2 mode. This is the FPT, which is for band 1 and for band 2. And this is this EPC model by using just this type of processes. I want to say now, I mean, this thing takes like, I don't know how many hours on a cluster, and these things, it takes like, I don't know, 0.01 seconds on my computer. So this is eventually is going to be really useful. And it works really well. So for this mode, actually, those papers saying that you can forget about everything that is relativistic and stick to this type of processes is correct. We can do the same thing for interband. So now you do scattering between band 1 and band 2. And again, it works pretty well. I also, comparing the model to this DFPT, I want to also point out at this point that the interband matrix elements are pretty large. And you can actually, basically, you can do the same type of transformation from taking this matrix element and going to the relativistic bands, and you get that the interband matrix elements are of the same order. So that was a nice check. Now, as I said, for the mode that we were interested in, this is not true. So I'm doing the same thing. I plot the coupling for DFPT. The model works really, really poorly for both intraband and interband. So at this point, we were like, okay, this TU is just not sufficient. We are missing something. There is some processes that this ferroelectric mode is inducing, and they are probably relativistic. And this we already speculated in this paper. So what we did now was do a little bit better. So you can extract, actually, you can write down the symmetry allowed terms and extract them by Wannier function. So you put like some kind of frozen mode in your system. So you put the mode that you want, and you extract the amplitudes for the different processes. So this is the non-relativistic one. This is, spin flip, so relativistic, and this is sigma z, also relativistic. And the answer is yes. So the mode is 2. This shows the ratio between the relativistic to the non-relativistic. So mode is 2 has, the 3 of them are basically less than 20%. But for mode is 1, this is the ferroelectric mode. I mean, there is a huge relativistic term here, has a really strong relativistic matrix elements. And then the nice thing about this model also is that you can analytically extract all these, in principle, all these interaction along any direction. Good, so now that we know that we have these relativistic terms, we have extracted them, we go back, and now we project, including not only TU, but also the relativistic ones, and this is the result. So this is DFPT, intraband and interband. This is the toy model. It works really well now. And the strength of this model is it's not a KP type model. It's not it's a lattice model. So when you go to higher Fermi energies and do not stay close to the, let's say, small k regime, you can do the same. Still, I don't have to do now any fitting anymore. I have everything I need in my system. And so when I go to much larger Fermi energies and I go to larger Fermi surfaces, it still works surprisingly well. And like something that now one can use this type of interactions, like mapping of the interactions, because now I can map it in the entire Fermi surface, like in under 0.1 seconds, is, for example, extract this coupling experimentally, which to the best of my knowledge has not been done until now. So I'm working with together with Damian Peltz to look at cone anomalies, and for that you need this type of expressions. And then I just want to say a few words about pairing. So I have, studied the coupling in all glorious details. So it was a few years ago pointed out that this is a special coupling in the sense that if you look at the Cooper channel, you get attraction in the S wave, but you also get attraction in P wave and D wave. It's subleading, but it is attractive. And this, just to connect to the previous talk, so in the previous talk, the reason you got S plus minus, D wave, and all these momentum-dependent interactions came from the propagator, which in that case is the chi spin and chi charge. In this case, the momentum dependence, so even if you keep this momentum independent, the momentum dependence comes from the vertex. So it's this K here that will, for example, give you attraction in P channel. Anyway, so now there is in principle possibility to having attraction in the P wave. As far as I know, there has not been any claims about that in this system. There is a very recent paper that claimed doing this non-reciprocal transport that they have evidence for an attractive spin triplet interaction. I leave it there. I'm not an expert on this non-reciprocal transport, so I cannot really judge. But that's one claim there. And then I just wanted to say that, of course, you can solve the pairing channel and look at lambdas and so on, but even without doing anything, with the type of coupling strengths that we are getting from ab initio, which is of the order of 60 MeV, all the calculations were done in other works for STO, and it has similar numbers. So in principle, I would say that this platform has hope for getting TC also in bulk samples, which, by the way, are apparently hard, very, very hard to get, to dope these samples in bulk form. But at least the coupling, so I would say the coupling to this mode is a good candidate to provide pairing in this system. And then I said something about orientation dependence, so we thought, okay, this is in the heterostructures, we're doing bulk, maybe this is a bit of, but let's look at how the EPC looks like in the different relevant cuts. And I just want you to see here that for the 3 different cuts, intraband, interband, the numbers are basically the same. So from bulk calculations, at least, there is nothing that this soft mode does that would distinguish between these 3 different orientations. On the other hand, there is all these reports that surface phonons may be relevant, and so we've been doing bulk stuff. I'm very lucky to have some of the leading experts in the world in San Sebastian and Bilbao who do all these slab calculations, so they are now working on seeing how the mode changes in surfaces. And then in the last minute or so, I just want to say a few words about the poly limit. So now I'm not gonna care about the pairing mechanism. I'm not gonna care about, whether I have, yes, one surface or the other. Just to remind you that experimental fact is that when you put a critical field in the superconducting sample and you compute or you know at what field these superconducting states should be killed, you find factors of up to, say, 10 larger fields. So I'm going to mention two mechanisms without anything fancy like triplet and so on, where you can get that, because you have strong spin-orbit coupling. So the first one that we proposed in this paper, because time is up. It won't let me go. I feel like I'm 5 again. Time is up. It's so funny, I get this like red. This is the last slide. Let me finish the last slide, please.
If anyone has a question while we fix this technological problem, please go ahead.
Wait.
Okay, so the problem was the operator.
Yes, so the first one, just want to mention quickly two mechanisms. The first one is we have strong spin-orbit coupling. So if you look at the electrons, I didn't say this because it was not needed at the time, but it turns out, oh, that was me, I think. Yeah. It turns out that these are J3 half quasi-particles here. Okay, so you get that. You have an effective L equals 1 of the orbitals with the spin 1 half. So this is like mapping it to Px, Py, Pz. And this we've done in like, I don't know, third undergrad. And so it turns out that in this particular case, the orbital moment and the spin moment are anti-parallel, so they cancel. So that means that you have extremely small moments, or quasi-particles with extremely small moments. So this idea that, oh, you're going to apply a field and the electrons are going to align to it, if your electrons do not have a moment or have a very small moment, you can't really couple to it. So superconductivity can survive to much larger fields. That's basically the idea. And the second, and I want to say I was very happy to see this. So we proposed this idea back in 2023. And there was a very recent preprint saying that they can only explain their magnetic, like their critical fields due to a near cancellation between orbital and spin moments. So I think there is some evidence that this might be a relevant mechanism. Nevertheless, I want to say another one that one should have in mind when you have strong spin-orbit coupling and you are in the dirty limit. So these systems are in the dirty limit. So if you have strong spin-orbit scattering, there is this KLB due to Clem, Luther, and Beasley from, I don't know, 75, long time ago, where they proved that in that regime also basically the spin paramagnetism gets hindered and superconductivity can survive up to much larger in-plane magnetic fields. And what we did was, okay, let's see if we can, using this formalism, fit the experimental data, and it works beautifully. So at this point, it could be that in these systems you can have such high critical fields surviving, or such robust superconductivity against critical fields, either because of this disorder effect, or the fact that you have reduced moments, or a combination of the two. We cannot, unfortunately, discriminate between the scenarios. So with this, let me quickly summarize. I've explained how to get a spin dependence electron-phonon coupling, and I would claim that KTaO is a good platform to get strong matrix elements that have, that are not just spin independent or the usual spin independent coupling. I also saw that it is quite robust. The coupling is quite large. It has strong relativistic terms. Looks promising for pairing, but on the other hand, there is no orientation dependence as seen in the experiment. It could be that there is something there that we are missing because we are certainly not including any surface physics. And I also discussed some mechanisms that this should be relevant for any system with strong spin orbit to get robust superconductivity versus magnetic field. And with that, I thank you for your attention. We're almost done for the day, and I'll take questions.
Questions? Gosh.
That one's even farther away than Ian.
Now I'm up here.
Thank you, Maria.
You're welcome.
So my question is regarding is there a general way of maybe understanding the possible pairing symmetries that a superconducting gap would have based on the different form factors that the electron-phonon coupling has? So you've shown us some like a zoo of several different kinds of form factors that these G's of K could have, and perhaps then my question is if we could associate maybe some kind of form factors with these pairing symmetries.
Yes, so the answer is yes. Once you have the form factor, then you can look at the channels. So I showed a bunch of them, but actually so kx sigma y minus ky sigma x, it's actually this. So this one, for example, gets this type of channel. So it's not like you get only attraction in one channel, you get attraction in several channels, actually. And then now I was cheating a little bit. Actually, I keep writing this, but for this system, it's probably a lot more relevant because we have J equals 3 half quasi-particles to use J matrices that are 4 by 4, and this is something that I'm thinking about now. So you start from the matrices that have 4 by 4, then you write the form factors, which now instead of having poly matrices, we'll have the corresponding irrep, which in this case would be the J matrix that has T1G, and then you derive the entire thing. But yes, in principle, you have the form factor, and then you write, or you look at the channel that is attractive, and in general, you will have several.
So if I can just make a comment and then ask a question. I think there is a theorem, that was proven by Philip Bryden showing that even when you have multiple, as long as it's electron-phonon, S-wave has always two wing. I think that agrees with what you're saying, right?
Yes. So as you see, like there is a hierarchy, but S-wave is leading, yes.
Now, my question is, did you solve the pairing problem with only the non-spin orbit coupling term?
No.
That term looks a lot like a loop current term.
Yeah.
And in that term, I don't think you're ever going to get attraction in the P wave.
Yeah.
So even though they may give similar things, I think without spin orbit coupling, it may not be a good pairing mechanism.
It could be, yeah. It could be.
But
so
we don't know that yet.
I don't know that yet. The only thing that I've known is categorize carefully what are the couplings in the system. And now the next step is what type of pairing do they give. Yeah. So the only thing I can say for now is for this one.
Sure.
Has been, yeah.
More questions? That's okay.
Thank you. So a follow-up question. This reminds me a little bit about nuclear superfluidity. When you have this quadrupolar vibration of the nucleus, and then you can have a pairing in the D-wave channel.
Yeah, that's L equals 2, yeah.
Yes, and then if you solve this has been done many years ago, if you solve the self-consistently with the transfer matrix, you can even have a pseudo gap.
I see.
Do you expect to, are you looking at this direction?
No idea. But, I mean, I don't know. I'm going to say I don't know. But in that sense, so it sounds very, very similar to this problem, right? Now, in this case, it would be L equals, well, 0 or S wave, or if you look at P wave. And then, yes, see what the, why is it the pseudo gap is obtaining in that system from, it's local. Then I don't know. Yeah, then I don't know. Because this is more standard pairing. There is nothing.
More questions? If not, let's thank Maria one more time. Our last speaker of the session is going to be Rob.